So, to wind up this chapter of the system of particles and rotation, rotatory motion, etc. Now we discuss one of the most interesting things, the rolling motion, the motion of wheels, etc. There are several examples, the motions of cylinders, etc. Without slipping. So we'll look at that. Now, what we have is a disc which is rolling and going forward from left to right, and we can see that rolling motion is a combination of the rotation and translation. The two motions which are taking place in rolling, of course the slipping is avoided here. The translational motion is the motion of the center of mass of the body, and this motion is depicted in the velocity of the center of mass, v center of mass, which is the translational velocity of the body. This is, it has been shown over here, the velocity of the center of mass, and it is parallel to the surface, the level surface. Level surface. This is a level surface, and it may be offering some friction. Okay, the level surface. So V center of mass is parallel to level surface, and the rotatory motion is about its symmetric axis. This is the axis over here passing through its center, and of course it is going through the board. Okay, the axis is coming out of the board, or the axis is going into the board, that's immaterial. It is the symmetry axis of the body under rotation. So what we have to consider is, there are two salient points, P0 and P1, one at the bottom, which is the only point in contact with the disc, rotating disc, and one at the top. P1 is at top, and one is the point in general, P. So these velocities can be said to be the velocity of the center of mass plus Vr, which is due to rotation. So I can also write that from our previous knowledge that Vr, the immediate velocity of any point under consideration, the magnitude of this is equal to Vr, which we can write as R omega, where omega is the angular velocity and R is the distance of that point under consideration from this center C. Okay, so this I am writing here as R2 for this case. Vr is perpendicular to Cp2. Vr is perpendicular to Cp2 because this motion is a kind of a immediate circular motion. So you know that the velocity vector is perpendicular to the immediate radius vector Cp2. So I can write whatever I have discussed just now, we can write very simple that it is sum of the center of mass velocity and Vr, the other velocity. So the velocity V2 over here is said to be equal to the sum of the two velocities. One is the center of mass velocity, which has been shown over here, and the other is the velocity due to its immediate radial distance from the point C under consideration. Now, V2, the result of this and this. You can see V2 is equal to V center of mass plus X, and it should have been a vector here. Okay, so this is like this, and V2 is perpendicular to P0, P2. Any location of this, it will be always perpendicular, so that we can say that the angle over here is 90 degrees. And the instantaneous axis of rotation, is the line passing through P0 and which is parallel to omega. Naturally, this, if I take it as a vector, then this velocity is out of the board. So this is out of board, and the instantaneous axis of rotation is also out of the board. Okay, so now we apply the relations that we obtained there for the 2 points P0 and P1 at the bottom and at the top. At P0, the linear velocity Vr, due to the rotation, is exactly directed opposite to the center of mass, opposite to the velocity of the center of mass. That is, if the velocity of the center of mass is in this direction, then the contribution of the Vr is in the opposite direction, and they therefore cancel each out. So the condition which has been defined, that while a rotatory motion takes place, this point is momentarily instantaneously at rest, because the two velocities, one because of the center of mass and the other because of the rotatory motion, at this point they cancel out each other. And we can write the relation, which is a scalar relation, that the velocity of center of mass is equal to r omega. This is because the P naught here has to be instantaneous rest. Okay. Similarly, if we apply it here at the point P1, then we find that at the point P1, the velocity V1, which will be there, this will be, the velocity over there will be a sum of the two velocities, because both of them are in the same direction, the velocity of center of mass and the velocity due to its position. So this r omega plus Vcm, and r omega itself is equal to Vcm, and therefore it turns out to be 2 times the velocity of the center of mass, and it is directly parallel to the level surface. So the exercise is very simple, and we can sum up that when there is a rotation of a disk on a level surface without slipping, then different points on the disk have different linear velocities. The center of mass of the system has got a velocity which is equal to V center of mass. The velocity over here is V center of mass minus V center of mass, which is equal to 0, and here the velocity is V center of mass plus V center of mass, which is equal to 2 into V center of mass. So that way we come to an end of this relation, rolling motion, and we'll now talk about the kinetic energy associated with the rolling motion. So we just calculate the kinetic energy of a rolling motion. Rolling of a disk, rolling of a cylinder, rolling of any body. So here, because the total kinetic energy of the rolling motion, which comprises of rotation as well as translation, this total kinetic energy will be equal to the kinetic energy of rotation plus the kinetic energy of translation. Let us write this kinetic energy of rotation as k prime, k dash, and of course the kinetic energy of translation is half mv square. Okay, where k dash is equal to half I omega square, where I is the moment of inertia of this body and omega is the angular velocity. So I can write, summing up together, I can write this relation that k is equal to half I omega square, the rotational counterpart, plus half mv center of mass, because velocity of the body is equal to the velocity of center of mass. Now, I is equal to mk square. We define the radius of gyration of any rotating body is given as mk square, where k is the radius of gyration. Of course, it is in meters. Also, as v center of mass is equal to r omega, I can write omega is equal to v center of mass divided by r. And if I substitute these values in the previous equation, I get half. For I write mk square. For omega square as v center of mass square divided by r square, plus of course half mv center of mass square. And if I take this half mv center of mass square, which is the kinetic energy of translation, then what I get is a formula which I can remember, which you can remember, which anybody can remember. It is in words, the kinetic energy of the system, translational kinetic energy of the system, multiplied by k square upon r square plus half. I'll make applications of this result in the next example. Okay? K is equal to half mv center of mass square plus k square divided by r square plus 1. Okay, now let us take an example of rolling motion. So here is a very simple example oft solved in most of the books. The example is that a ring with k square is equal to r square, that is the radius of gyration square is equal to the radius of the ring square. A solid cylinder, k square is equal to r square by 2, and a solid sphere where k square is equal to 2 by 5 r square. They are made to roll down the same inclined plane without slipping. Their radii are equal. The radius of the ring, the radius of the cylinder, the radius of the sphere, they are all one and the same. We will see that masses may be different because it doesn't matter. Now the question is, which body reaches the ground with maximum or minimum velocity? So you can see that the velocity of the body when it starts rolling is equal to 0, and the velocity when it reaches here is v is equal to v. And in the process, while it is rolling down the inclined plane, which makes an angle theta with the horizontal, there is a fall of the body, apparent fall of the body through a distance h. So the potential energy of the system is maximum over here, and the potential energy of the system is minimum at the ground level. Then we write the equation which we had derived just now about the total kinetic energy of the system, which is equal to half mv square, the translational kinetic energy multiplied by k square upon r square plus 1. Okay. Then the second thing that we are going to use is that the change in the kinetic energy is equal to change in the potential energy, which is apparently mgh. M is the mass and g is the gravitational field and acceleration due to gravity. So if I write this, I equate this k to mgh. Write this equation as it is, and then find that the m and m are going to cancel out. M and m are going to cancel out. So what we have, the v square will become equal to 2gh divided by this k square upon r square plus 1, which is put in the bracket here. And now if I apply the data for the ring where k square is equal to r square, we find that v square will be equal to 2gh divided by, these are two equal, so it is 1 plus 1, which is equal to 2, so 2 and 2 cancel out and v becomes equal to under root of gh. For the solid cylinder, k square is given as r square by 2. If I substitute the things, I get v square is equal to 2gh divided by half plus 1, which is 2 will go up, so it becomes 4gh divided by 3, and therefore the velocity, corresponding velocity when the cylinder reaches the ground level is equal to 4 by 3 gh under root. And similarly for the solid sphere, k square is equal to 2 by 5 r square, so the velocity square becomes equal to 2gh divided by 2 by 5 plus 1, which is equal to 7, and 5 goes up, so 10 gh upon 7. Let us call these velocities as v1, v2, v3. Okay, just like this. I call this v1, let me call this v2, and let me call this v3. What we see that these velocities, these values are under the under root condition. So this gh I can write as 21 upon 21 gh. Just taking the LCM, and here v2 I can write as 28 upon 21, multiplying both sides by 7, so 4 7s are 28 gh under root this, and third case I multiply this 7 by 3 and 10 by 3, so I get 30 gh upon 30 upon 21 gh. Since the denominators are the same, for the sake of comparison I can take this as this is 21, 28 and 30, which are in the increasing order. So the maximum velocity and therefore the maximum kinetic energy on reaching the ground level, that will be maximum for the third case and minimum for the first case. And thus we can say, you can also ask what is the ratio between V1 and V3, V2 and V3, etc., etc. We can find out from here. So that is about an application which is oft quoted in many a book, and therefore I also thought it relevant to discuss out this with you. Okay. So to wind up this, I take a special case, want to discuss with you the rolling motion of a cylinder on an inclined plane, and this is a rough surface naturally, so that we'll see as to what is the condition of the motion without slipping. Now we know that in the rotational motion we have an angular velocity omega, and the velocity of center of mass of the body I have taken just as v, and this v is equal to r omega. These are some of the results which we have known, so we are just recalling and putting it there. Now let us see what are the forces which are acting in the system. So one of the forces is, which acts here, is the normal force, okay. The normal force, which is N, normal reaction. Second actual force which is acting in the system, that is the cylinder, is the gravitational force, which is vertically downwards. And it has got two components. One component is mg cos of theta, which is in the normal direction. I just write this here as mg cos theta, because this is the angle theta. This also becomes, you can prove it, not needed how to prove it, but you can prove it, it's easy. I'm not proving it, okay. So mg cos theta in the normal direction and mg sin theta along the incline, parallel to the incline, okay, inclined plane. Then the third force is the frictional force, which is up the inclined plane. This is the frictional force which holds it, opposes the motion, the rolling motion, okay. The force acting parallel to the plane, there are two forces. One is mg sine of theta this way, and the other is F. So naturally, because the rolling takes place, therefore this mg sine of theta must be more than the frictional force F. And we can write it by definition from the Newton's second law, that this force acting parallel to the plane is m dv dt, which is equal to mass into acceleration, according to the second law. Also, now we have to calculate the torque. So I d omega over dt is equal to torque. I am just writing the scalar form, and this is equal to F multiplied by R, because this is R and this is F, like this. Of course, there are two other forces, but these forces are passing through, okay. The cylinder rotates with omega about its instantaneous line of contact. The instantaneous line of contact is here, okay. About the instantaneous line of contact with the inclined plane as its axis of rotation, Now N and mg, they pass through the center of mass of the system, center of mass here. Therefore their contribution to the torque will be equal to 0. They have hardly any contribution to the torque. So therefore the sole contribution is because of F, and I d omega over dt, which is equal to torque, is equal to Fr, where R is the lever arm, okay. R is the lever arm, and in this case R is also equal to the radius of the cylinder under rolling motion. So continuing, we have we know that alpha is the acceleration, is defined as d omega over dt, and I alpha is equal to Fr, okay. I alpha, the moment of inertia into the angular acceleration, is equal to force into R. So I can write I alpha is equal to Fr, and from there I can obtain F is equal to I alpha over R. It's a very simple thing, just manipulation of things. Now when I substitute in the other equation that we had, then Ma, the force, becomes equal to mg sine of theta minus I alpha over R. So this is the net force which is acting in the system, and then I can write it again as I upon R, because alpha I can write A upon R, and therefore this becomes equal to, for alpha I write A upon R, and I get this relation. So now there are two terms, MA and I upon R square A. So if I take this A as common, then I get M square plus I upon R square, which is mg sine of theta. Mg sine of theta. Interesting. Okay. So A is written as mg sine of theta divided by m plus I over R square. So from there I can write the value of alpha as, and I divide this numerator and denominator by m, so I get 1 here plus I R square into m, or mr square. So I get the value of alpha as g sine of theta divided by R 1 plus I upon mr square. From where I can write the value of f as, the value of f is equal to I upon R g sine of theta divided by R 1 plus I upon mr square. Now for the given cylinder which is rolling down, we have the moment of inertia as equal to half mr square. Okay, so this gives us the value of A as g sine of theta divided by 1 plus half mr square upon mr square, which cancel out. This half is left over here, so it's 1 plus 1 by 2, which is 3 by 2, so 2 goes up, and we get for the value of A 2 by 3 g sine of theta, 2 by 3 g sine of theta, and the value of alpha, because it is equal to A upon R, so I divide this and get 2 by 3 R into g sine of theta. So naturally, and then the value of f I write from here, and I get f is equal to I divided by R, the same thing, g sine of theta, and R 1 plus, for I write now again half mr square, so I get here mr square and mr square, they cancel, and I get 1 plus half here. So ultimately I can write this as equal to half mr square g sine of theta, whole thing divided by R into R, 1 plus 1 upon 2. So R square and R square, they cancel out, and we obtain the value of f as equal to 1 by 3 mg sine of theta. Okay, see, the f has to be much less than mg, because it is divided by 3, and sine theta cannot take a value more than 1. Okay, the value of sine theta is also much less than 1, so therefore the force that we obtain is equal to 1 by 3 mg sine of theta. Okay, so now I am rewriting the value of F, the force, the frictional force, 1/3 mg sine of theta, and we also recall that N, the normal force, is equal to mg cos of theta. They equate because there is no motion perpendicular to the direction of the incline, so these two have to be equal. Now if I divide F by N, what I get? Mg and mg cancels out, sin theta upon cos theta is tan theta, so 1/3 of tan theta. Okay, so this is F by N, I get as 1/3 of tan theta. Now the maximum force that is applied is equal to the coefficient of static friction multiplied by the normal force. So therefore we can write that this relation, that 1 upon 3 tan theta will be smaller than or equal to mu s. Equating it to mu s, what I get is that the maximum value of theta of the incline over here, that will be tan inverse of 3 into mu s. Tan inverse of 3 into mu s. And if the theta exceeds that value, then of course the rolling will not take place, and of course there will be maybe some rolling, but it will be slipping of the disc or the cylinder down the inclined plane. So friends, with this case study, with the example that we took, and we discussed the rolling motion of bodies, cylindrical bodies. Also we took an example where a spherical body is going down the plane, and before that we learnt about the moment of inertia, the torque and their interrelationship. A lot of things we have done in this chapter. The chapter which is taken as the distributed masses in the form of a rigid body, etc., etc., angular momentum, the conservation of angular momentum, and how to find the value of I, how to find the value of tau, etc. So we are now equipped to deal with many other similar problems, and it's for you to search the problems, to apply yourself, and I hope with the training that I have given to you here, it should be possible for you to apply yourself and obtain the results. The next chapter we come down in the next lecture, and that is about the beautiful but the weakest force of nature, and that is the gravitational force. Remember, we have the two nuclear forces, strong nuclear force and electromagnetic force, the weak nuclear force, and the gravitation, that order. And the forces are many times the weak nuclear forces are strong as compared to the gravitational force. Electromagnetic are stronger as compared to the weak nuclear force, and the strong nuclear force which holds the protons and neutrons inside the nucleus, that is. But these two forces, remember, I just want you to recall and remember that these two forces are very, very short range forces. Short in the sense that it's of the order of the size of nucleus, and the size of nucleus is 10 to the power of 15 to 10 to the power of 14 meters. So there they are very effective, and they don't disturb our normal life. Our normal life is disturbed by the gravitational force and several orders of magnitude more, which is the electromagnetic force, which gives us the frictional forces and many other forces, stability, etc., etc. So we will talk next about, and remember, in the beginning I did take Newton's law of gravitation. I will elaborate on that. We'll learn many more things, the variation of small g, etc., and we will enjoy further. Thank you very much.